Good afternoon, class. We are looking at statistics practice test number 2. Module 2 covers chapters 4 and 5. And here's chapter 4, probability. All right, so let's look at a couple of definitions. A simple event is a sample space is. Those are the definitions we want to look at. A simple event is an outcome or an event that cannot be further broken down into simpler components. A sample space is the set of all possible outcomes or simple events of a probability experiment. If two events are mutually exclusive, also known as disjoint, the probability that both will occur is 0. So events A and B are disjoint or mutually exclusive if they cannot occur at the same time. That is, disjoint events do not overlap. The notation is P of A and B equals 0, or P of A, we may use the notation, or the intersection of the event. This looks almost like an N, probability of A intersection B, known as the AND event, and it's equal to 0. In other words, A intersection B must be an empty set. So to add this concept, and the symbol is phi, which represents an empty set. This is not 0. This is 0. Okay. Distinguish between the two. The probability of an event is always between 0 and 1. So P of A is N of A over N of S is the probability of event A, and it's between 0 and 1. Can it be 0? Yes. Can it be 1? Yes. Can it be negative? Absolutely not. Can it be larger than 1? Absolutely not. The only time that it may be, it had like 1.00000001, the total, okay, if it's due to round of error. So the sum of the probabilities of all final outcomes of an experiment is always 1. So the sum of the probabilities of all outcomes in the sample space is 1. Summation of P sub I is 1. Again, the only time it may be like 0.9999 or 1.00001 is just due to round of error. That's why if we keep the exact answers, it won't happen. Here's an experiment we can look at. Rolling a die. All right, so a regular die is a 6-sided with numbers 1, 2, 3, 4, 5, 6 that you can find on each side. Sample space. The common die has 6 faces. We usually call the faces 1, 2, 3, 4, 5, and 6. And here's the set. A simple event, any individual number such as 1 or 5. A compound event, any event having more than one outcome, such as odd numbers would be 1, 3, 5. So here's the sample space. Here's a couple of examples of a simple event. Here's an example of a compound event. The number of combination of n items selected n at a time is, well, and the number of permutation of n items selected 0 at a time is. We want to calculate those, so let's refresh everyone's memory about both concepts, permutation as well as combination. Permutation is an arrangement of objects in a specific order. Order matters. Example, the letter arrangement of ABC, which could be ACB, BAC, BCA, CAB, and CBA, are all counted separately as 6 current permutations. For example, if you use it as a code, ABC is different than ACB. When n different items are available and R of them are selected without replacement, the number of different permutations or their counts is n factorial over n minus R factorial. The notation that we use is NPR. Sometimes they use it in this format, P and R. That means permutation of n, choose R. R is always less than or equal to n. The formula is n factorial over R factorial times n minus R factorial. I put the R here. This one needs an R. I'll put it in a moment. This needs an R. Now, this is for the combination. No, this is for the permutation and this is for the combination. Combination is a grouping of objects. Order doesn't matter. So, 2 things. Order matters, becomes a permutation, n factorial over n minus R factorial. Combination, order is not important. For example, when we say ABC, it doesn't matter which one of those we are interested in those 3 letters, becomes a combination, n factorial over R factorial times n minus R factorial, or the permutation divided by R factorial. So, having said that, if we want to do this, we are going to replace the R with n. And by the way, the notation for combination class, for combination, you can use this or you can use this one. Also, sometimes they use a parenthesis like so. So we use the formula and we replace the R with n. So n minus n is 0. 0 factorial is considered to be 1. And n factorial is identical to n factorial. They cancel each other. The final answer is 1. If I want to calculate the permutation, we are going to go with this formula, and we are going to replace the R with 0. By the way, as far as the definition of this is that it becomes n times n minus 1 times n minus 2 all the way to the number before this, which is n minus R plus 1. So for example, if it's 8, you can stop at 9 here. So for this case, in this formula, we replace the R with 0. When we do that, the numerator is n factorial, n minus 0, n factorial over n factorial. That is also equal to 1. A pizza parlor offers 10 different toppings. How many 4-topping pizza with different toppings are possible? Well, order is not important. It becomes a combination. The reason order is not important is because you're ordering pizza. It doesn't matter. You want 4 different topics, and let's say one of your choices is mushroom. It doesn't matter when you order that as the first one, second, third, or fourth. That's why it's a combination. Order is not important. So with the formula here, n is 10, R is 4. Now, of course, you can use a calculator to do the math. I'll show you later on. But if you were to simplify this, this becomes a 6 factorial. And to simplify this, if you're doing it completely by hand, you can first, the bottom one, the larger one is 6 factorial. So the top make it 10, 9, 8, 7, 6 factorial multiply. The 4, you don't have a choice but to go with 4 times 3 times 2 times 1. And so why did I stop at 6 factorial? Because I can drop those. Um, 4 times 2 is 8. 9 divided by 3 is 3. So the answer is 10 times 3 times 7, which is 210. So it can easily be done by hand. Nobody expects you to do that, especially for large numbers with hand, but you should be able to understand the concept. How many 6-letter code words can be made from the 26 letters of the alphabet if no letter can be used more than once in the code word? And pay attention to the code, and that means order is important because AB is different than BA, and it becomes a permutation. With the permutation formula, N being 26, or however many letters we choose. In this case, there are 6 of those. And again, what matters is that if you're doing this type of question, if you write this and then the answer is good enough, because this is telling the reader, you know what's going on. It would be nice to set it up like this and the final answer is fine. Please understand, this is like 20 factorial. So 26 all the way times 21, and then 20 factorial cancels out the bottom 20 factorial. So this is 20 factorial. That's why this goes all the way up to the number before this. So this number is 20, so up to 21. And it's a huge number, 165,765,600. Answer the following. A quiz consists of 3 true-false questions. How many possible answer keys are there? Write out the sample space and tree diagram. Well, first and foremost, the sample space is the number of outcomes per stage, and you raise it to the power of the number of stages. So in this case, true false gives us how many possible solutions? Only 2. There are 3 questions. That is the number of stages in essence. So 2 cubed or 8. 2 cubed or 8. A tree diagram is truly helpful. So you have a couple of branches. The first branch is T, true, and the second one, F, false. Now, you want to be consistent. If the top branch is T and the bottom is F, keep it that way. Not that it matters, but if you keep it consistent, it's easier to keep the track. So TF and all the way to the end. So right here, you see you have TTT. Over here, you have TTF. Over here, you have TFT, TFF, FTT, FTF, FFT, FFF. And that's stage 1. That means the first question, stage 2. Second question, stage 3. Third question, I can even write that at the top of it. So in other words, this is question 1, let's say. Question 2, question 3, And that's the sample space. Again, T is the first one, F is the last one. If you keep it the way I told you, it's very easy to keep track of everything. The sample space for tossing 5 coins consists of how many outcomes? Write out the sample space. Again, I'm refreshing your memory that N of S, the size for the sample space, is the number of outcomes per stage, and we raise it to the power of stages. The number of outcomes, in each case, we have only 2 outcomes, H and T, heads and tails, 2 outcomes, 2 outcomes. How many stages? However many coins. In this case, we have 5 coins. So N of S is 2 to the power of 5, which is 32. By the way, don't mix it up with 5 squared, which is 25. So 2 to the 5th power, 32 outcomes. Now, I'm going to show you the tree diagram for 4 because there's no room here. So, and again, you want to keep it consistent. H, all of them. The H is at top and the T is at the bottom. And then the last one, notice T. But we want 5, so I need to add one more stage. So first and foremost, this is stage 1, coin number 1, stage 2, coin number 2, stage 3, coin number 3, and stage 4, coin number 4. We are going to add the 5th coin, and again, HT, and this is stage number 5. So now if you look at the very top branch, you have H. There are 5 of them because there are 5 coins. This one would be H, T. And if I put the last one in, I get T, H, T. So we can write out the sample space. Pay attention to the very first one. There are 5 H's, 1, 2, 3, 4, 5, because there are 5 coins. And look at this one. All H's except the last one. And look at the very last one. T, and there's one more that I didn't have room to put. There are 5 of them. Total of 2 to the 5th, or 32 outcomes. Could somebody read this question, please?
A random sample of 100 people was asked if they were for or against the tax increase on rich people. Of 60 males, 45 were in favor, and of all females, 22 were in favor. Write the contingency table and answer the following questions. If one person is selected at random, find the probability that this person favors the tax increase on rich people. This person favors the tax increase on rich people.
Excellent. Now, anytime you're given a question like this, you got to be able to come up with a table. So you want to be very careful what you need. So you come up with the following table. Males, females, total. For tax increase, against it, and again, total. And I'm giving them letters because it's easier for representing the probability. M for males, F for females, T for tax increase, A is against it. Just make up any initials that you want. Now let's put in all those numbers that we are given, and if we put that properly, everything will fall into place. The very first number is 100. We have a random sample of 100. So the total size is 100. So please understand, this is the total for this one and this one. This is the total for this row and this row. And it's the grand, you can call it grand total of 100. So we want to fill this up. The very first number, okay, was asked if they were for or against the tax increase on rich people. Of 60 males, so males, 60, 45 were in favor. So where do we put the favor? 4. And of all females, we're looking at this row, 22 were in favor. 22. Now, this is good enough for us to fill up the rest. First and foremost, what number comes here? Add these two. 45 and 22, the total is 67. What number comes here? The total is 60. So 60 minus 45, 15. So we have number 15 here. What about here? Well, first let's figure out this one. 60 with what number is 100? Because the total is 100, this number becomes 40. 60 plus 40 is 100. Now this is 40. This is 22. This must be 18, right? 40 minus 22 is 18. Let me write it and then I erase it. So first add these two, 67. Then I need 40 here, right? Then 67 plus what number? We need 33 here. Then 45 plus what number is 60? 15. And now 22 plus what? 18. So I hope you see it's very easy to fill up the rest, and we put everything else in there. Now we are ready to move on. This person favors the tax increase. We're going to write P of T is N of T over N of S. I like to start with the denominator and the sample space. In this case, the sample space is always the total unless it's a conditional probability. We'll discuss it in a moment. So it's N of S. So this is 100. Out of those 100, how many are for tax increase, 45 plus 22, or simply 67? So 67 over 100. I mean, this happened to be the same as 0.67. If you want to go to decimals, you want to make sure that you be careful as you go from fractions to decimals, because fractions are normally exact and decimals may or may not be. All right. So that's what we got. This person is a female. P of F is N of F over N of S. Obviously, N of S is a total of 100. How many females? So look for F. The total is 40, or 22 plus 18, however you want to put that. So it's 40. So 40 over 100. Now, a fraction must be simplified. Of course, this is 40% or 0.4 if you were to go with the decimals, but otherwise, you can drop a common factor of 2 and you get 2/5. Okay. A fraction. So is this the correct answer? Yes, but it's not a finished job. I can't emphasize this enough. In math, you always put it in lowest term. This person opposes the tax increase on rich people, given that the person is a female. Another way of putting it, if this person is a female, she opposes the tax increase. There are two different ways of writing this, so I want you to be familiar with that. So this is called a conditional probability. Anytime you see the concept of a given with this format or this format, and I'm going to remind you, probability of A given with this line segment is red given. Is probability of A intersection B over probability of B. Probability of B given A is the same intersection, but this time we divide by A. So you divide by the second part, in this case P of B, in this case P of A. And so now, given the person is a female, so probability opposing, we are using A given F. Please understand, according to this formula, we have probability of A given F, which is probability of A intersection F over probability of F. according to this formula. Now, it becomes N of A intersection F over N of F. So what's important to understand, anytime you have a conditional probability and given, the total sample space of 100 is no longer there. So your total sample space shrinks to what comes after the given. After the given is female. So now the denominator is N of F, which is 40. So always write the denominator first. I think it's important to understand the sample space has changed, has shrunk to 40. Now, how many of those 40 are against the tax increase? That is the concept of intersection. Intersection of this row and this column. If you were to draw a line here, if you were to draw a line here and a line here, they would come together at this number, and that's 18 over 40 and must be simplified to 9 over 20 or 0.45. So pay attention to the conditional probability. This person is a male given that, that he favors the tax increase on rich people. So is a male. So probability of M given, that means this is, if you go with this probability of A given B, so this is M given that he favors the tax increase. The tax increase, we use T. So probability of M given T. And according to this formula is probability of A intersection T over P of T, or N of M intersection T over N of T. Again, an easy way to look at this concept is to understand this becomes this. And in essence, N of T, what comes after given, becomes the new sample space. So no longer the total is there. So what comes that is the tax. So how many favor the tax increase? 67, that's the denominator. Out of those 67, how many are males? 45. So you can go directly to that or say 45 over 100, 67 over 100, they cancel each other. So in other words, this corresponds to this, whereas this one corresponds to this. Simplification of that. And of course, if you have to go with the decimals, I put 4 decimals, you may need to use more. All right, that's the same question. The next part, this person is a female and favors the tax increase on rich people. First and foremost, the only time your sample space of 100 shrinks is when it's a conditional probability, meaning given. So this is still 100. So basically, you want the probability of F, which is females, okay? This person is a female and favors tax increase. So probability of F intersection T. So here's F, here's T. So F and T, 22 is in common. So 22 over 100. Again, as a fraction becomes 11 over 50, as a decimal becomes 0.22, as a percentage becomes 22%. This person opposes the tax increase on rich people or is a female. So let's write the or statement. Probability of A or F, or probability of A union F, is probability of A plus probability of F minus probability of A intersection F. It's important to understand the or means in the addition concept in probability. And Another way of writing this, P of A is N of A over N of S, P of F is N of F over N of S, and this one is N of A intersection F over N of S. So, or you can just have a large fraction bar, add these two numbers, subtract this. Now, I want to make sure we understand why this is the formula. So this person opposes the tax increase on rich people or is a female. So against it or female. So if you look at the against, we have a total of 33. If you look at the females, we have a total of 40. But number 18 is in common. 18 has been accounted for 2 times, once for the row, once for the column. That's why we take it off. So 33 total here, 40 total here. 18 has been accounted for 2 times. That's why we take it out. Once it becomes 55 over 100. We simplify it to 11 over 20 or 55% or 0.55. Are the events females and opposes the tax increase on rich people independent? Explain. Now, I want to give you the definition of independency, but it's pretty hard to really follow. Here's the independence definition. First and foremost, if you look at this, probability of A intersection B becomes the product of these two. So probability of B times probability of A given B. Again, I'm assuming everybody can see this cross product. Okay, cross product. So probability of A intersection B from here is probability of B given A times probability of A. So that's by definition of conditional probability. Now, events females and opposes the tax increase on rich people are dependent because occurrence of one of the events does affect the other event. Otherwise, does affect, not does not. So that's a definition, but it's a very vague definition. So how do you take care of that definition mathematically? You look at the following. If two events are independent, the conditional probability becomes a marginal probability. So let me just write that. Independent, if two independent, probability of A given B becomes probability of A. So let's look at probability of A given F and probability of A, for example. So we notice probability of A given F. If you want to take the easy way out, F just after the given part has a total size of 40. So we no longer deal with the 100 original size, but rather it has been shrunk to 40. And out of those 40, how many are A's? That means against 18 over 40. So that's the conditional probability. What is probability of A? Well, that's 33 over 100. Are they identical? If they are identical, the two are independent. Otherwise, they are dependent. Well, since I use dependent here, actually, that's fine. Now, you could try, I'm going to leave this for you. You could try probability of F given A and show that it's not equal to probability of F. So I'm going to call this number 1. I'm going to call this number 2. You don't have to do both. One is good enough. Are they mutually exclusive? Well, I hope you remember the concept of a mutually exclusive when they have nothing in common. So they are not mutually exclusive because a person can be both female and opposes tax increase on rich people. Again, the proof is that you look at the probability of A intersection F. Probability of A intersection F. If it's 0, they are mutually exclusive, but it's 18 out of 100. And that's the proof. So let me just quickly fix this. So whether you want to prove dependency, independency, mutually exclusiveness, or otherwise, you have to show it with numbers. So this is numerically proved, this is numerically proved, because sometimes the definition is not good enough. I want to answer the following. Find the probability of getting the outcome of tails and 2 when a coin is tossed and a die is rolled. Well, they are independent events because they have nothing to do with each other. Probability of A intersection B therefore becomes probability of A times probability of B. I want to make sure we understand that if we go back to the previous page, what we had here, this is the general case. When they become independent, probability of A given B is A, probability of A, probability of B given A is probability of B, and therefore, if 2 events are independent, probability of their intersection is simply multiply the 2. So in this case, tails and 2 is the probability of tails, which is 1/2, times the probability of 2, which is 1/6. As you recall, a die is a normal die is a 6-sided with numbers 1 through 6. So the answer is 1/12 precisely. If you have to change this to a decimal or percentage, you want to do it accordingly. A classic counting problem is to determine the number of different ways that the letters of personnel can be arranged. Find that number. First, I want to explain something to you. Can somebody read this permutation rule? Please.
Permutations rule. Distinguishable permutations. When some items are identical to others, the number of different permutations order counts when n items are available and all n of them are selected without replacement. But some of the items are identical to others is found as follows. N1 are alike, N2 are alike, and Nk are alike.
Perfect. So we use the formula n factorial over n1 factorial times n2 factorial all the way times n sub k factorial. So what we need to do first is that we have 1, 2, 3, 4, 5, 6, 7, 8, 9. N is 9. Now we start counting. P is 1, E, there are 2 of them. R is 1, S is 1, O is 1, N, there are 2 of them, L is 1. So you really have to count that very carefully. And so following this formula, the top is 9 factorial. The bottom, all of them are 1 factorial except 2 of them. So in essence, you have really 9 factorial, and the bottom 2 factorial is the same as 2 because it's 2 times 1. So 9 factorial divided by 4 in essence. 9, the bottom is 4. And you can use a calculator, of course, 90,720 ways of writing it. A box consists of 14 red and 36 blue markers. if we select 3 different markers randomly, what is the probability that they are all red with replacement? Well, probability of a red is n of r over n of s. So we have 14 divided by the total of 14 plus 36 or 50. So 14 over 50 or 7 over 25 or 0.28. This is for 1. Probability of 1 red. If we want 3 of them, that's in essence probability of R1 intersection R2 intersection R3. That means the first one is red, the second one is red, the third one is red. And because they are with replacement, that means independent. So P of R1 is this number. P of R2 is the same. They're all the same. Just multiply 7 over 25 or 0.28 by itself 3 times or raise it to the third power. So P of 3 reds is the same as P of 1 red to the third power. And you can write that such. And by the way, because the denominator is 25, it becomes a terminating decimal. You don't have to do the rounding. Now, look at this part. We are repeating the same question except without replacement. So what is the probability that they are all red without replacement? Draw a tree diagram and label each branch. Okay, so that is extremely important to understand, everybody. Well, if we want 3 red, that means probability of red, the first one, which is R1, times the probability of R2 given R1, times probability of R3 given R1 intersection R2. You don't have to write it in this fashion that a lot of people really follow that and understand that. But that is the proper notation. Now, the first one, very simple, 14 out of 50. But what happens here? It's important to know first and foremost, because it's without the replacement, now we no longer have total of 40 plus 36, 50, but rather we have 49 markers left. And if the first one was 14, now we have only 13 red, and it goes down in the same manner. So 14 out of 50 times 13 out of 49 times 12 out of 48. Again, without replacement, which means we are dealing with the dependent events, dependent events. And so this is the exact answer, and this is with the decimals, and I want to discuss a different method and the tree diagram. But again, we need to understand what happens here. So you can say probability of all 3 reds is, okay, the denominator first. We have total of 50 combination. I'm going to pick 3. And the probability that is the total size, that's the sample size. What do we want? Out of those 14, we want to pick 3. And by the way, really the proper way of doing the numerator is combination of times combination of 36, choose 0, because we don't want to choose any blue, right? The reason why I want you to understand this, for example, if they said, what about we want 2 reds and 1 blue, then this would be 2 and this would be 1. That's why I want you to understand that. However, this will be number 1. You can calculate combination of 36, choose 0 becomes 1. So it has no bearing. And that's the same answer as this one. As far as the tree diagram is concerned, so the red, the very first stage, the probability of red is 14 out of 50, blue is 36 out of 50. When we go to the second stage, so which means the second peak. Now this one, in this branch, one red is gone. First of all, in this stage, the denominator, look at it. It's all 49, one less than that. The last one, all the denominators are 48. If you look at this one red is gone and it becomes 13. In this one, another red is gone, it's become 12. But if you are here, okay, so all the blue is left, 36 over 49. You go down here, the red, none of them is gone, so 14 out of 49, but over here, one blue is gone and it's 35 over 49, and this one, all two is gone and 34 over 48. So I want you to study this, make sure you understand this and the concept of without replacement. And by the way, if the question doesn't mention with or without replacement, almost without exception means without replacement. If you're picking 3, you're not going to do the replacement. So I did it on purpose, but like I said, even if none of them is written, that means part B. Pay attention to that. If the probability of winning the race is 5 over 12, what is the probability of losing the race? Well, complementary event. First of all, what is given probability of, let's say, W stands for winning. The complementary event says probability of A bar or A naught or A complement is 1 minus probability of A. So probability of losing is 1 minus the probability of winning, which is 1 minus 5 over 12, and everybody knows it's 7 over 12. Seven over 12. What are odds against winning? So let's discuss the odds. The actual odds against event A, we write it O against A. That means we put A complement, is probability of A complement over probability of A. This is by definition. It is expressed as a form of A colon B or A to B, or A and B are both integers. So with that being the case, O odds against winning, O of W naught, so O of L, so P of L over P of W, which is 7 over 12 over 5 over 12. 12 and 12 cancel each other, 7 to 5. 7 to 5, or you can write it as a fraction. If the payoff odd is listed as 6 to 1, how much profit do you make if you bet $10 and you win? Again, let's look at the definition. The payoff odds against event A, payoff odds against event A is net profit to amount of bet. That means net profit divided by amount of bet. So take a look at this one. If you do the cross product again, net profit is the product of these two. Payoff odds times the amount of bet. And so 6 to 1, this means 6 times 10, $60. When two different people are randomly selected from those in your class, find the indicated probability. Assume birthdays occur on the same day of the week with equal frequencies. Probability that two people are born on the same day of the week versus probability that two people are both born on a specific day. It doesn't have to be Monday. You can say Monday, Tuesday, Wednesday. It works the same way. But the key is understanding the same day is different than saying on a specific day of the week. So When we have the same day, no particular day is specified, the first person can be born on any day. What about the second person? Probability of the second person born on the same day as the first one is 1 out of 7. So the first one can be born on any day. But the second one, having the same birthday, is 1 out of 7, same day of the week. So basically becomes this number, because it's 7 over 7 times 1 over 7. So 1 times 1 over 7, which is 1 over 7. And the reason I want you to look at both questions simultaneously, because we want to distinguish between this is extremely important, and this one. And again, you can change it to Friday. It still works the same way. A specific day of the week. Now, the first person has a probability of 1 out of 7 to be born on Monday. The second person, the same thing. We are going to assume, of course, independency. So therefore, you're going to multiply them and you get 1 out of 49. So the product of these two. Again, pay attention to this versus a specific day of the week. How many different auto license plates are possible if the plate has 2 letters followed by 4 numbers? So the very first thing I want you to notice, we have 1, 2, 3, 4, 5, 6 spots. And for this one, we have 2 letters and 4 numbers, and there are no restrictions. 2 letters would be what? 26, and then times 26, and the numbers would be 10, 0 to 9, 10, right? The number of digits. So 26 squared times 10 to the power of 4, 26, 26, 10, 10. I can write it there so you can, because you really have to see why this is 26, 26, 10. And so that's what you get for the first part. Part B, 3 letters, no repeats, followed by 3 numbers. So we have 3 letters. That means this is 26, but this one is not 26, 25, because we can't repeat it. 26, 25, 24, we're done. Now followed by 3 numbers, 10, 10, 10, or 10 cubed. So 26 times 25 times 24 times 10 cubed. Again, I'm not interested in the final answer. I'm assuming, everybody can put it in the calculator and calculate that. The point is, how do you arrive at it? This shows the justification of your work. Again, put it into a calculator, come up with a large number. 4 letters, repetition allowed, followed by 2 numbers, no repeat. So when you go here, it's all 26, 26, 26, 26. There are 4 of it, 26. So you have 26, 26, 26, 26, 4 of it. Then you have 2 numbers, but they can't repeat. So you have 10, and then it goes down to 9. So 26 to the power of 4, 10 times 9. Four places. So we have 4 spots. Each character is either a letter or a number. I can put a letter here or a number. There are 26 letters, 10 digits. They add up to 36 alphanumerics. So I can put 36 here, 36 here, 36 here, 36 here. So 36 to the power of 4. And again, obviously everybody can calculate it. It's not a big deal. You have to put it to calculate. In a first grade school class, there are 10 girls and 8 boys. In how many ways can we do this? The students finish first, second, and third in a foot race. Assume no ties. Well, order becomes important. Order becomes important when you do this. And therefore, it's a permutation. So P and R, in this case, P of how many? We have total of 18 kids, and we want to choose 3. So P18, 3. And you can say 18 times 17 times 16, do the math. Or if you use a calculator, okay, for the factorial, this is how you do it. For the permutation and combination, you enter the value of n. In this case, you put 18 and then n, PR, 3 and 40, 896 is the answer. So NPR 3, because we want to choose 3. Again, you don't have to necessarily do this by hand, but it's important to understand this. It's a permutation and VAR. Or you can think of it as 3 spots. They can't repeat. The girls finish first and second in a geography contest. So again, order is important, and we are just dealing with girls. So let's go back here. So we are just dealing with 10. Okay, so it's the same thing, permutation, but this time it's permutation of 10, choose 2. Permutation of 10, choose 2. Why 10? 10 girls. Why 2? Because we're interested in the first and second. So 10 times 9, 90. Or you can use a calculator with a permutation. 3 boys be selected for lunch. See, there is no restriction. First and foremost, we are not dealing with 18. We have only 8 subjects here. Okay, and we want 3 of them. Order is not important. It's a combination of 8, choose 3. Combination of 8, choose 3. So 8 factorial over 3 factorial times 5 factorial. And you can write this as 8 times 7 times 6 times 5 factorial, drop the 5. Again, I'll show you if you were to do this by hand. The top is 8, 7, 6, 5 factorial. So the 5 factorial you keep, the 3 factorial, you put 3 times 2 times 1. This cancels out the 6. These two cancel each other. 8 times 7 is 56. So it's very simple to come up with that. Let me clean it up. You can do this by hand. Now we want 6 students for a team, hockey team. So basically, order is not important. And we are looking at a total of 18 kids. We want 6 of them. Combination of 18, choose 6, which is 18 factorial over 6 factorial times 12 factorial. And again, you can just use a calculator for the number is getting larger, and you get 18,564 different ways. 5 students be selected. Specifically, 3 boys and 2 girls. So if you just stick with that, you want 3 boys out of how many? 8. Order is not important. Therefore, all right. So order is not important. It's a combination. And from 8, we choose 3. From 10, we choose 2, combination. So the product of the 2. So